I think the last part of the introduction got cut off, so it's present and future of Rollup interoperability. And in particular, I will be talking about something called a shared liquidity bridge and the ability to have synchronous composability between rollups. But first of all, let's start at the beginning. So I assume most people here probably know or heard about rollups. Rollups are horizontally scaling Ethereum. It's this beautiful idea where as you add more applications to Ethereum, you can add dedicated servers that execute for those applications. An application may also be a virtual machine that hosts other applications, such as all the rollups that are listed on this slide. The great thing about rollups are that they enable natural sharding of computation across applications. And it also enables powerful nodes to help weaker nodes verify the state, meaning that you can have a very, very diverse set of nodes participating in layer 1 security and a smaller set of more powerful nodes participating on the rollup layer. It also enables virtual machine diversity. What are some of the, where's there room for improvement though? Well, one of the main downsides of rollups today is the impact they have on interoperability of applications across different rollups. And this in particular leads to more liquidity fragmentation than you see in just the Ethereum L1 today, where apps can easily interact with each other and liquidity is more consolidated. So what are some of the issues and challenges with rollup interoperability, and specifically bridges, which is the simplest form of interoperability? Well, one is speed. So in general, when moving assets between rollups, one needs to wait for L1 finality, and not even finality, but also something called settlement, which may be longer than just data finality. The settlement could include, for example, the fraud-proof window if it's an optimistic rollup. Another issue is of what representation does the asset have once it's bridged over? Is it a wrapped version of the original asset, or is it fungible with native assets on that chain? So if you bridge ETH from one rollup to another, do you get native ETH on the destination rollup or not? That can affect liquidity, fungibility, the ability to use it in DeFi protocols, etc. And finally, an issue is synchronicity. So, and bridging is one thing, it's a form of asynchronous interoperability, but could you have contracts on one rollup, make method calls across rollups? And this would allow you to do things like flash loans or limit orders, etc. Synchronous composability of applications, I would say, is one of the hallmarks of Ethereum. The ability to make function calls between smart contracts. You could, for example, have a trader contract that implements some kind of smart contract wallet, and it could execute a limit order on an automated exchange where it only makes the trade based on what the price is at this time. That today is not possible across different rollups. If you had the trader application on one rollup, it would not be able to do this in an automated exchange that exists on a different rollup. So you would have to have a copy of the automated exchange on the same rollup as the trader contract, and that divides liquidity. But before we get to talking about synchronous composability, let's take a look at asynchronous interoperability, which is predominantly how, is the way in which rollups interoperate today. So there are two things that I want to focus on initially. One is cross-chain message passing, which would allow you to, for example, lock an asset on one side and then mint a version of it on another side. Issues with this are that it's, again, as I mentioned earlier, slow. You have to wait for finality of the sending rollup to consume the message. Now, applications can trade risk for speed by accepting pre-confirmations, for example, from a trusted committee. Now, one natural party to accept more risk rather than an application is a specialized actor, and these are called cross-chain intent solvers. Liquidity providers are probably the easiest way to move assets between chains. They hold balances on two different chains, and they could even execute for both chains, and they can assume the risk of releasing money on one side before it actually settles on the other side. So this is what cross-chain intent solving looks like. You have some solvers. The solvers may be competing for this opportunity. A user signs an off-chain request, and the solver will consume a transaction that pays to some settlement contract on the first rollup. As soon as it is comfortable trusting the finality of that transaction, it can execute a transaction on rollup B where it sends money directly to the user. And this is great for fungibility. The downside, there are two downsides. One, the solver has to hold a balance of the same asset on both chains, so say native ETH on rollup A, native ETH on rollup B. And if the solver wants to move funds very quickly, then it will take the risk of posting transaction B before transaction A is truly final on rollup A. It may know information that allows it to do this. For example, it's running a node for rollup A. Perhaps it trusts the sequencer of A, so it doesn't even wait for the L1 to finalize the data. And then it will wait for the chains to eventually settle, and that cross-chain settlement will be in the form of a cross-chain message from rollup B to rollup A. One way of strengthening the security of this is to introduce something that makes it more difficult for the sequencer of rollup A to equivocate. And one of the sources of risk for the cross-chain solver is that the sequencer may say that it's going to do one thing and then decide to post something else to the L1. If you introduce an external BFT consensus, for example, that doesn't need to execute, but just prevents equivocation on what data is posted to the L1, then this can provide some additional security, especially to a cross-chain solver that is running a full node for rollup A. So as soon as it knows what data is going to be finalized, then it can compute, as any full node for that rollup would, the state of that rollup. So this is the way it would look, as the solver's risk is reduced, and it can now fill the request faster and cheaper because it gets a certificate from this fast finality layer on the fact that the transaction A on rollup A will eventually be made canonical on the L1. Now, how do we avoid the need for liquidity providers? Well, I'm going to talk about something called a shared liquidity bridge. But first, let's take a closer look at asynchronous message passing without trusted intermediaries, because this is going to be required for understanding the concept of a shared liquidity bridge. So, asynchronous message passing could happen in the most straightforward way using the L1 itself. Now, the most naive way would be to withdraw assets from rollup A and actually get them back on the rollup on the L1, and then using the normal deposit function, deposit into rollup B. But there's something better than that we could do, which is rollup A has an outbox, a message outbox and inbox. Rollup B also has a special message outbox and inbox. And both rollups have a state root on the L1, and part of that state root is a Merkle root for this outbox and inbox. So rollup B could send a message to rollup A by sending a message to its outbox for B, and this would eventually be recorded in this outbox B Merkle root. The sequencer for rollup A can, at the start of a block, fill the inbox of rollup A with new messages that were sent as a part of this outbox on rollup B, and it can provide Merkle proofs for the correctness of those messages. And so the inbox A would read from the outbox B root on the L1 to verify these messages. So this is a way of sending messages between the rollups, right, without actually having any L1 transactions. However, some things to note about this. Rollups must wait for L1 finality to read an inbox message. If the sending rollup is optimistic, in fact, the receiving rollup must not only wait for L1 finality, but must wait for a fraud-proof challenge window to read an inbox message. Or alternatively, it could receive a validity proof. Right? This doesn't mean that the sending rollup needs to be a ZK rollup. It could still be an optimistic rollup, but yet there's a third party that is computing validity proofs for that optimistic rollup as well that are not used for settlement, but are simply used for these cross-chain messages. And so that would allow it to only wait for L1 finality on the data. It wouldn't have to wait for the fraud-proof window. A receiving rollup could choose to take more risk and accept inbox messages with some faster pre-confirmation. For example, maybe it will trust a signature from a sequencer. But then it would take risk that sent messages revert. In fact, this creates an attack vector for malicious sequencers to cause damage as a result. Individual contracts could also potentially independently take that risk-speed trade-off with pre-confirmations, but it is not at all without risk. Let's look at a slightly different way that message passing could work, introducing something that I call an L1 cross-check. So with this setup, the rollups no longer need to read Merkle roots from the L1 or verify proofs. They just optimistically trust the sequencer for correct inbox messages. But we use the L1 itself to protect against a malicious sequencer that would pass the wrong messages. So here, the L1 is storing the Merkle roots of these outboxes and inboxes and is directly checking consistency between them. So in a bit more detail, there's an old outbox and a new outbox. And the consistency check that's happening is that the inbox for this current block, on rollup A matches the old outbox from the last block on rollup B. And this would be done, this consistency check would be done. Of course, we could use fancier data structures like history, accumulators, etc. I'm trying to simplify here. But the important thing is that this consistency check would eventually be done on the L1 itself. Now, there's some important caveats of this in addition to the benefits. So let's look at some pros and cons. So on the pro side, there's no need for checking Merkle proofs inside the rollup. Messages from a trusted sequencers could be included without delay. If the sequencer on one side can verify a validity proof of rollup B on the other side, then it could even safely include messages without waiting for L1 settlement and vice versa. But the cons are that the rollup settlement is now interdependent. This can affect the withdrawal liveness. So the withdrawal liveness of one chain is now dependent on the liveness of the other chain. In particular, a receiving rollup settlement time is now dependent on the sending rollup's fraud-proof window, unless it receives a validity proof. And rollup A full nodes are now uncertain about their current state, unless they either also run a full node for rollup B or receive fast validity proofs, and those, again, could be off-chain. So things are, the picture is a bit less fraught if you have very fast ZK proofs. It also simplifies things on the L1 because you don't need to have one rollup wait for the fraud-proof window of another rollup. So in this case, both rollups are verifying validity proofs. And these validity proofs, if they can be made available very quickly, they may be posted to the L1 less frequently due to compression concerns. But if they're produced very quickly, then the rollup full nodes of each side can be aware of the state of their own chain quickly, as they should. Moreover, if you have validity proofs being created, then you can apply optimizations such as proof aggregation, where you have some aggregator service that aggregates the validity proofs for both chains. And in fact, this aggregator service, why stop there? It could do even more. It can even include in its proof aggregation the consistency check between the outboxes and inboxes of either side. And the only thing that the L1 does is verify this proof aggregation. Now, you still have a coupling between the liveness of withdrawals on the two rollups, right? Both rollups have to wait for this aggregator service to produce this aggregated proof, but each of these rollups do now the same thing, which is just verify this one aggregated proof. Another benefit of aggregation is that as the number of interacting rollups grows, then the number of cross-checks between inboxes and outbox grows quadratically, so aggregation can help a lot for the efficiency there. So now that we have this message passing as a building block, let's look at a shared liquidity bridge, which is an application of message passing. So the concept of shared liquidity bridge is that you have, I think that, again, there's many different ways to present this, but this is the way that I think is the cleanest to present it. You can look at a shared liquidity bridge. It's essentially its own rollup. It's an independent third rollup. And it has a bridge root, and users can deposit tokens into this bridge root. The shared liquidity bridge, as a rollup, will manage a table that holds the accounting of where each token sits on the, in this case, 2 different rollups that are sharing this liquidity bridge. And a user, when it deposits an asset into the shared liquidity bridge, would specify the destination. For example, 50 ETH goes to some address on A, 25 DAI goes to some address on B, etc. Now, using as a building block this message passing that I've discussed in the previous slides, now you can have when a Rollup B user wants to withdraw from Rollup B, it can either withdraw directly to the L1, or it can send a message to the shared liquidity bridge that would actually move the asset directly to Rollup A. And in this case, it would initiate a deposit message to Rollup A, and it would update inside its table the respective balances of ETH on Rollup A and Rollup B. Withdrawals in this case would go through the shared liquidity bridge, always, but we could also make this fancier and enable 2 types of deposits into a rollup. One through the shared liquidity bridge, and one through the Rollup's contract or native bridge itself. In this case, each rollup would need to maintain a table of balances, noting its balance from the shared liquidity bridge and its balance from the local bridge. And upon a withdrawal, it would deduct either from the local balance or the shared balance. So what about synchronous composability across rollups? Well, the starting point is to emulate function calls with synchronous message passing. So let's first give a sketch of how this works. This is not what we actually are going to do. We do not want rollups to have to wait for each other and send multiple rounds of messages. But if these if these contracts, in this case the trader contract and the automated exchange contract, by the way, this is really just a toy example, so don't look into this example too closely. It's intended to simplify things for educational purposes. But you have a contract on one rollup, a contract on a different rollup. If they were on the same rollup, then they could send messages between each other and wait for the other contract to process it and then return a message. This is how inter-process communication would work within one rollup. Across 2 different rollups, we don't want to send messages and wait. Okay, but if we could, then what would happen here is the trader contract would essentially initiate a message to this AMM on a different rollup asking for a price quote. It would get back the price quote, and this would lock the execution of that AMM, so nothing can happen on this AMM between when it gets the price quote and when it takes its decision to then bridge an asset over and actually trade it within the AMM. So now, with the message passing setup that we just had, there's only one change that we need to make, which is that instead of having the 2 sequencers on the different side independently populate the inboxes, you can have a coordinated sequencer. Either this is a coordination between 2 sequencers, or this is what people call a shared sequencer, that effectively unrolls the execution ahead of time to determine what messages should be sent between these contracts. And now it can fill in the correct inbox messages, right? So in this toy example, this limit order transaction would first perform a write to its outbox of price lock. It would then, it should receive back this message 2,999, but now it can read it. It can just execute a read immediately directly from its inbox, and then it can perform a third write to its outbox, 10. So it's basically just, it's verifying a transcript of what should have happened rather than actually, going through this inter-process communication in the forward direction. And the same, symmetrical thing can happen on the other side. Now, the coordinator could, of course, include wrong values in the inboxes. Say it puts 200 in inbox B, which is not what outbox A sent. It only sent 10. It could just omit transactions from one side. How do we prevent this? Well, it's no different than what we saw earlier in the case of asynchronous message passing with 2 independent sequencers. So to review, with optimistic rollups, right, you can have this cross-check on the L1. With validity rollups, it looks the same, but with validity rollups, you can additionally add this proof aggregation step where both rollups, verify an aggregated proof at the end. And so if the coordinator were to do something malicious, then this would eventually be caught because this aggregated proof would be incorrect. So I'm running out of time, but again, just to note, one of the downsides of this is that full nodes of rollups should always know the state. So, an important thing here is to have offline proofs that are really fast. It also helps to have a fast finality layer on the side that can help convince the full nodes on either side of the finality of transactions quickly before, waiting for L1 finality. So thank you very much, and that's the end of my presentation.